recording is a continuation of covering Dalton's laws of partial pressures for gases. And we're going to be looking at this relationship right here, where the mole ratio of one component to the total is equal to the partial pressure of that component compared to the total. So let's take a look at a picture first to explain this. Here we have one cylinder, 5 liter, that holds hydrogen gas. Here we have another cylinder that's holding helium gas. And if we combine these two in a second cylinder of the same sort, there's some interesting relationships that show up. First, let's take a look at what happens to the partial pressure. And this is the one that we've already talked about, where you see that P total is going to equal partial pressure of the hydrogen plus the partial pressure of the helium. You can also see that if we add the moles of gas, they are also going to be equivalent, so that N total equals the moles of hydrogen gas plus the moles of helium gas. The other thing we can do is we can look at the ratios. So if we look at the partial pressure of hydrogen gas and we compare it to the total pressure, and we're just going to call that P tote, we get 2.4 atmospheres divided by 8.4 atmospheres. And if you plug that into your calculator, you get that that is equal to 0.286. Now let's take a look at what happens when we do the same thing with the moles of gas. We're going to look at the ratio of the moles of H2 to the total moles. And this is going to be equal to 0.50 moles from right there over our total moles. There's the 1.75. And you plug this in and you get the exact same number. So what we end up with is the following relationship. If we know the ratio of one gas to the total, then we know the ratio of the moles to the total. And this turns out to be a very, very useful relationship here. So here it is restated here, where A is whatever gas we're looking at in particular, and this is your total mixture. So let's take a look at this problem here. We've got a tank that contains 6 moles of a mixture of hydrogen, helium, and nitrogen at 102 kPa. There are 2.0 moles of hydrogen in the tank. What is the partial pressure of hydrogen? So we are told that NT, that's our total, is 6.0 moles. We know that P total equals 102 kPa. And we know that NH2 equals 2.0. So let's use this relationship here. 2.0 is to 6.0 as the partial pressure of hydrogen is to 102. If you solve for pH 2, you have pH 2 equals 34 kPa. Let's put a box around this just to indicate this is the final answer. Let's try this one down here. A gas cylinder contains 8.0 moles of argon, 2.0 moles of nitrogen, and 2.0 moles of oxygen at 600 millimeters of mercury. What is the partial pressure of nitrogen in the tank? Well, we know that PT has to be all of these added together in terms of moles. So PT has to be partial pressure of argon plus the partial pressure of nitrogen plus the partial pressure of oxygen. And we also know that NT has to be all the moles added together. In this case, we actually have that. We have 8.0, there's our argon, plus 2.0, plus 2.0, for a total of 12 moles. We know that our total pressure here, PT, equals 600. So let's just go ahead and solve this. We know that we're looking for the nitrogen, so we're going to put 2 moles of the nitrogen over a total of 12 moles is going to be the same thing as our P nitrogen, partial pressure of nitrogen, over 600. 2 is to 12 as PN2 is to 600, and when we're doing sig figs, what we end up actually doing is we're going to set this to 1.0 times 10 to the second. Let me get that multiplication sign in there better. 1.0 times 10 to the second millimeters of mercury equals the partial pressure of our nitrogen gas. We're going to try a couple more problems. We're going to add another equality to this relationship here. We have the mole fraction of the gases. That's the partial moles of A compared to the total moles, and the partial pressure of A compared to the total pressure. We're going to put another factor in here, and we're going to say that these are also equal to the volume that is due to gas A compared to the total volume of the gas. So we're adding this factor right here. Well, let's look at this problem here. We have a mixture of gases with a pressure of 950 millimeters of mercury, and it contains 20% hydrogen and 80% neon by volume. What is the partial pressure of neon in the gas mixture? So we're looking at the neon. So we have that the volume of neon is 80% of the total. So we're going to have 80 over 100. We're doing volume due to A over the total volume equals, and we're interested in the partial pressure of the neon, so it's P neon divided by our total pressure, 950. And when we solve for that, we get that the partial pressure of neon is 760 millimeters of mercury. So you can put a box around this. Now, there is another way of seeing this. We can say that our P total is 950, and that 80% of this is due to neon. So we would convert the 80% to the fraction. So we would just multiply it by 0.80. And you get exactly the same answer. Let's take a look at this problem here. We've got a mixture of xenon and argon gas. It tells us 70% of the total gas pressure is exerted by the nitrogen. If the total pressure is 150 kPa, what pressure does the, well, let's change this problem here. Let's try that again. We're going to do xenon, sorry, typo on this. And this one's going to be argon. Let's cross that out. I apologize. All right, we've got a mixture of xenon and argon gas. 70% of the total gas pressure is exerted by the xenon. What pressure does the argon exert? Well, if 70% is due to the xenon, then we know that we have to have 30% due to the argon, because they've got to add up to 100%. We've got a total pressure equal to 150 kPa. We want to know what pressure is due to the argon. So we're going to take 30%. That's 30%. We're going to multiply it by 100%. 250. And when we do that, we'll get 45 kPa, and that equals the partial pressure of the argon. So here's another useful relationship right here. All of the ratios follow.